have to concentrate. Economic dispatch and optimal power flow are the two broad classifications of effective operation of power system. Economic scheduling is just to find out the optimal combination of generators for a station's load. Among the available generator in a plant, depending upon the schedule put on that station, how many of that station's generator, which out of that has to share certain megawatt as a schedule, is a decision based on the availability of resource and cost of production and demand how to address. On that basis, choosing up of certain generator to meet certain demand of the station for a certain combination hour. That kind of intelligent decision with the economy concerned to the generation and resource and optimization is concerned is known as economic scheduling. This schedule is only an cost-effective allocation of units only. The other part of which is this schedule do not confirm, guarantee whether the power which is being generated is delivered to the end user in a very low loss path based delivery or how it is being delivered is not concerned. Therefore, the another type of study in economical operation of power system is optimal power flow. The optimal power flow is a study of the given power system's load flow from the generating station to the dispatch or to the load. How is that routing of power takes place to deliver it to the end user to their subjected specification with least last path delivery. Here the most concerned here is effective delivery of the power. However it is being received from the generating area to the grid, how effectively it is reaching the end user with the path chosen or alternatives selected such that path delivery losses are minimal to the extent. Such an objective is kept and study is being performed if this particular route for a certain generating station to a certain load center is very effective, it shall be enhanced, it shall be used to deliver the power to the fullest capacity of its loadability, MVA transfer, etc. Here it is concerned with the delivery. How it is coming from where it is being generated is immaterial to this aspect. Therefore, these two wings are certainly two aspects when we combine them. The one aspect, economic concern to the generation and cost-effective way of generation using the resource. The another being the best and optimal path with that route. If the routing takes place to reach the load, it is very effective and low loss capacity delivery. When I combine these two, it becomes a security constrained optimal power flow, which ensures overall delivery of power to the end user in a very cost effective manner of its generation, distribution to the load center or to the end user. But this is easy to combine and say. On the operational aspect, it is not that easy. Whenever a certain path is chosen as the best path for the delivery, how do you ensure that particular path will remain for your service till the transaction duration? If there occur a fault, if there occur a failure, how would you reroute it once again? This is a concern to the optimal delivery. Therefore, the security of that selected path, reliability of delivery of certain megawatt to the load effectively for the committed duration become a very challenging task. Therefore, these all together run as security constrained optimal power flow, which ensures fail-safe operation. A certain path having certain transmission section between bus 1 and 2, 2 and 7, 9 and 11, like that. Imagine a route of delivery to a certain megawatt. If that route find a fault, a section one of the element in between opens due to fault. How do you meet the requirement of the load without affecting their reliability? There must be alternative path chosen. There must be a security concern taken around if this section fails. If this generator which is combined to generate goes out of your control, then how is that setting or how is that rerouting take place? This concern about the commitment has to be taken. In this due regard, to magnify this control, the economy of generation concerned concept, the optimal delivery of power to the load is concerned, there it becomes difficult to see to it that all the generators which are chosen are really there for your service. All the paths which you have identified do serve your requirement. In this due course of this, lot of study has to be done on the given power system. Computational mechanisms must be used to see to it that selected operation become cost effective. Then, again taking a small magnified view from the generation side point. Now I combined both aspects together as an security constrained optimal power flow, which has to be addressed by the power system operation and control concept concerned. Now, in line with this, a small focus if I do it, there when I have a generator combined from a certain generating station to meet certain demand of that plant. How is that among the available generator sharing up of load takes place? In broad terms, we said economic allocation should take place. The cost effective allocation of units on the generator by type, by capacity, by their characteristics, I must combine them so that such a combination should become cost effective. Yes, again in that, if there are 10 generators in a plant, how would you combine all the 10 for a certain demand? Is it economical to run all the 10 generators all the hours of a day or over a month? Definitely it is not going to become economical. Now I am concerned about how is that economics connected to a generation aspect of a plant be viewed still better way by focusing only on selected generator which must be keeping the target of generation as scheduled. That we consider as unit commitment. Unit commitment is a schedule. Commitment from the selected generators of a certain generating plant to meet the changing requirement of a plant, so that those identified generators are capable of taking the dynamic changes of the load and able to provide a megawatt as required in a very cost effective manner over minimum to the maximum capacity of their combination. Hence, among the available generators, only selected generators are chosen for this schedule. Then you might ask me, what about the remaining generator? Suppose there is a 10 generator in a plant, say 6 were committed for a certain agreement for a load of 1 week. What about the remaining 4 generators? Definitely they will be producing a certain megawatt as a dynamics or as per the requirement, but they are not compelled to the sensitivity that the first 6 which were chosen for the schedule were touched upon. It means to say, among the available generator, only selected effective, cost effective, functional generator which are very efficient in comparison for a certain megawatt from minimum to maximum were chosen. It is not to discourage 7th, 8th, 9th, 10th not to be taken. It is the generator. It is the least number of generators together in a string combined to meet a certain demand which are dynamically going to cope up and deliver the megawatt. Such an schedule we call it as unit commitment. Certain megawatt 0 to 100, another generator 0 to 200 megawatt. Like that, the connected generator together have a fullest capacity, sum of their capacity. certain working capacity, what right now they have been set and generating, add them, and minimum capacity, what minimum they can generate, PG min. So this schedule makes it possible. This is truly because on a given power station, the load curve, if I see, it is not a static load. It is from the minimum, rising pattern, falling, again rising, again low, peak, valley kind of pattern we'll find. According to that, it becomes very necessary for the power system operation and controller concerned to the generating plant tune or control the generations at each generator so that the effective utilization of the fuel takes place. It reserve it for the future, and such an set point surely make a cost effective operation to generate the megawatt and the losses in concern to make your P balance and Q balance. In this regard, unit commitment schedule takes a great importance. Hence, in this due regard, how a unit commitment schedule is understood so that that combination of selected generator result you very low cost of production of megawatt from minimum to maximum as it is graded. In this regard, let us say a simple method. We call it as a simple enumeration method. It is also known as a brute force method. What exactly it does then? There are two methods in fact. Priority listing method and a dynamic programming method, which you have learned in part in the earlier semester. So we are revisiting it in this current semester. It will be very advantageous for us to revisit from Dr. K. Umar Rao textbook perspective this time. Take an example which is shown. For a unit number 1, 2, 3, as in the slide, minimum generation is 150 megawatt, maximum generation is 600 megawatt. The fuel cost function of that generator is C1 given as 5610 a constant plus 79.2 P1 plus 0.01562 P1 square rupees per hour. It may be dollars per hour in some of the other textbooks which is available. No matter, it is called a fuel cost, in which P1 refers to megawatt obtained from unit number 1. If I insert that megawatt P1 in the position P1 and P1 square, it give me how much is the investment from this generator perspective for a certain P1 value megawatt in rupees per hour if I run it. Likewise, I have a second machine, minimum 100, maximum 400, C2 as a cost function. Like third machine, minimum 50 megawatt and maximum 200 megawatt and cost function C3. Now it becomes necessary to understand what unit or a combination of units should be used to supply a load of 550 megawatt in a most economical manner. See here, it comes under economics. How we would have solved it? We would have solved it by economic scheduling, taking care of DC1 by DP1, DC2 by DP2, DC3 by DP3. It's called as the equal incremental cost criteria. We have learnt it from Lagrange's optimization study. I should find it out as a common lambda. From that lambda, I have to find out what is the P1, P2, P3 schedule. Then it becomes necessary for me to run all the three. I should use the common lambda in each equation and get P1, P2, P3. But here is, among the C1, C2, C3, I am not confirmed. Let all the three be used. I am asking what is the best combination of these three units such that this 550 megawatt is addressed. The issue is something different. Earlier, economic scheduling itself is concerned. My target is use all the three machines. See to it that PD of 550 is addressed. That is the scheduling. Now I am not doing that. I am trying to map in the form of a table or a knowledge how C1 and C2 together provide a combinational output for a certain megawatt 0 to or minimum to 550 cost of their production. Then C1 and C2 and C3 when together get into what is the cost of production for certain megawatt minimum to maximum. This I am going to do analytically. So therefore, there is a small difference in approach concerned to economic scheduling finding out an optimal megawatt on each generator using all the set of generators in the combination. That is what Lagrange's optimization mechanism we have learned. In unit commitment, we will not be taking that. We will be finding out among the available generator for a certain step value of load, how is that combination 1 with 2, 2 with 3, 1 with 3, 1, 2, 3 together can provide their combinational support for the meeting up of demand has to be addressed. That we call it as unit commitment. The committed unit, how do they cope up with the changing demand or a certain demand most economically is a target we are trying to understand. Then it's called brute force method or a simple enumeration. It is an exhaustive work. Series of calculation have to be done. Optimal value from that has to be taken from the calculation. Let us see how these three machine problem be addressed. Let's see. The solution for this is very simple. I have a table. The table, small table shows units 1, 2, 3. Their minimum capacity and maximum capacity. I will try to list down. The first unit is having a minimum of, I can just go back and come. It is having a minimum of 150 megawatt. You can see here. This is 150 megawatt and it is having 600 megawatt maximum. 100 megawatt minimum, 400 megawatt maximum. 50 megawatt minimum, 200 megawatt maximum. In that regard, let us see how it is being titled. 150 minimum, 600 maximum. 100 minimum, 400 maximum megawatt, and 50, 200 combination. Then using these three units, I can develop a table. Let us say unit 1, unit 2, unit 3. If all the three units are in functional, 2 raised to 3, I will have 8 combinations. So n is the number of units and 2 raised to 3, 2 raised to n stands here means 8. Therefore, let us make a table like a binary table how you write. Combinational circuit 0, 0, 0, 1, 0, 0, 0, 1, 0. Off I consider 0, on I consider logic high. Like that. Table you can generate. All the three units are off. Only first unit is on, rest two are off. And only the second unit is on, first and last units are off. The third combination of single combination is first and second off, only third is on. Then I'll use the 2 in combination. First and second on, third off. Second and third on, the first one off. First and third on, second being off. The most important combination of fullest capacity is all the three on. I'll get 8 combinations. Using this combination, what I can do, I can set up 0, 0, 0, 1, 1, 1 like that. Then I can generate this value as minimum generation of this unit being 0 by combination. 0, maximum is 0. It is because all these things are off. Off, off, off. Then definitely no one is in service. I will find 0, 0 megawatt. Do this combination is able to meet your 550 megawatt demand? Surely no. So it is called infeasible state of combination. Then only unit 1 is on, unit 2 and 3 were off. During this state of operation, unit 1 is on, its minimum capacity is 150. You can see here. Minimum generation is 150, maximum possible is 600. Then I will segregate. Its combinational state by contribution is, suppose next column I have combination of units, minimum combination column, maximum combination column, and I have sharing up of P1, P2, P3 for this load. So I have 550 as a target on P1 only. Here I am not given any target, like let me go back. Do this machine is given a condition minimum of 150, maximum of 600. What is my load? 550. It is able to cope up. Hence, I will write here 600 is the maximum, 550 is the target. It can definitely share. and other two are not in the practice. This 550 megawatt, if I want to generate from the machine number 1, what is the cost of production by this setup? I have to use this fuel cost function. In this fuel cost function, if I substitute 550 in the P1 and P1 square place, I'll be getting cost of production. That's what is here. 53,895. So it's very simple. Substitute this megawatt in the position of P1 in the fuel cost function, obtain the value as is. This is the combination result of 1. The second next combination of single machine is off, on, on. Only machine 2 is chosen. Look at this combination status. Minimum is 100, maximum is 1. Can this meet your requirement alone? Definitely no, because requirement is 550 and you cannot meet. It is infeasible state. You can see here. Then similarly, the third machine is alone on 50 and 200 megawatt. This is also infeasible. Infeasible state says that particular machine is not able to cope up for your current demand, 550 in this case. Surely I'll find the first combination, all are off, infeasible, and machine 2 alone on, infeasible, machine 3 alone on, infeasible. This is due to the situation of the generator's capacity. It's called capacity constraint based infeasibility. Next, the combination of on, off. Here we have 1 and 2 together combined. Let's see, when 1 and 2 together combined, the minimum of 150 from this machine, minimum of 100 from this machine. What is the total combination minimum here? 150 plus 100, 250. You can see here. When machine 1 is on, 2 is on, minimum pair combination is 250. The highest contribution what they can share is 1000 megawatt, because 600 plus 400. I can just write here. Then it become a question. How is that 550 megawatt demand is addressed from these two machines? There is a numerical data which is 295 megawatt be shared by machine 1, 255 megawatt be shared by machine 2. You might ask me how you can get this so directly, easily. Definitely it is not that easy. I have to combine this megawatt 550 as a target. How I have to do? Machine 1, machine 2. I should consider for the calculation, because that is the only combination I am working. Machine 1 on, machine 2 on, machine 3 off in that state. And use this C1, C2, get the value of lambda. It is called dC1 by dP1, dC2 by dP2, and equate it. You will get as one equation in terms of P1 and P2. Then another equation for you is P1 and P2. P1 plus P2 together should serve your demand of 550. Solve those two algebraic equations. You will have one algebraic equation from dC1 by dP1 equated to dC2 by dP2 and get the value of P1, P2 after solving P1 plus P2 equal to 550 equation. That's what that equation result you the optimal equal incremental cost criteria based solution for 550 megawatt for machine 1, machine 2 being 295 megawatt from machine 1 and 255 megawatt from machine 2. You got a solution here. So these two values, if I respectively position in P1 and P2, and I'll get cost of production from machine 1, cost of production from machine 2, which you are very familiar. So that results me the net combination cost of 54,712 rupees total investment. So this is how the combination cost is worked out. Then this combination is effective. What is the range? 250 minimum megawatt production to the fullest capacity 1000. But my load is 550. For a 550 megawatt load, this combination definitely fulfill. The one was only generator 1. It was fulfilling. We don't know whether this I have to choose, this I have to choose. I have to check all the combinations initially. So I will find the combination together will provide a production of 550 megawatt at the investment of 54,712 is the cost. Then the next table row, if I go off, on, machine 2, machine 3 together fulfilling the requirement. At that time 150. 150 is the minimum megawatt. You can see here 150. and 400 plus 200, it is a 600 megawatt as the total highest combination. You can see 150, 600. So these two machines combined together to produce a 550 megawatt very surely. Then when I solve these two equations, how I should solve? I go back. C2, C3. dC2 by dP2, dC3 by dP3. If I utilize solving those two in pair with P1 plus P2 equal to 550, I will get solution for P2, solution for P3. That is on equal incremental cost criteria. So when I solve that, I am quite sure 150 megawatt to 600 megawatt range of production for a certain 550 megawatt, it results me 400 megawatt be encashed from machine 2, 150 megawatt be from machine number 3. So therefore, you might ask me, why not the other way? Why not there is an incremental or a higher capacity on machine 3, a lower production on machine number 2? It all depends again on fuel cost function. The cost of fuel, what is put on a machine 2, machine 3, matter you. The coefficients over here determine which machine is relatively cheaper in production of certain megawatt for your combination. And here, I am quite sure machine 2 finds its best scope for higher production than machine number 3. So that is put with 400 megawatt and 150 megawatt. Together 550 is served for us. Then cost of production of 400, cost of production of 150 from respective machines, machine 2, machine 3, if I substitute and obtain, it results a value of 54,188. See here, the combination is having superior than the previous combination. Let us see once more, because still we have further combination. Machine 1 and machine 3 can serve. So machine 1, 150 and 50. The minimum possibility 200. You can see 200. And machine 1 and 3, 600 plus 200, which can serve you 800 megawatt. You can see here, it is 800. Therefore, it is like this: 600 plus 200, 800, the fullest capacity, 150 and 50 result to 200. So 200 to 800 is the range played by machine 1 and machine 3 if they are in combination. Therefore, for these two machines, if I put a task of 550 megawatt, how do they share? Again, I will solve machine 1 equation, machine 3 equation after dC1 by dP1 equated to dC3 by dP3 and taking care of P1 plus P3 equal to 550. When I solve these two optimally, it results in a loading of 500 megawatt on machine number 1 only and 50 megawatt on machine number 3. You can see the minimum capacity of production being 50 from machine 3. That is what is the forced value. Therefore, the situation is very clear here. When I had only machine number 1, it was fulfilling my 550 with a cost-effective way. When my target is to pair the committed unit 1 and 3, the megawatt on machine number 1 automatically decreased to 500 and other is shared with a 50. Why not less than 50? It might be again question for you. It is an infeasible because 50 is the minimum capacity what the generator 1 can develop for your load. So below 50 infeasible. Above 200 impossible because of constraints of capacity concern. Therefore, in this due regard, when I put them in a pair, 500 megawatt is allocated to machine 1, 50 megawatt is allocated to machine number 3. Together fulfill your requirement of 550. Again, same work I have to repeat. When I have 550 megawatt put on these two, 50 megawatt on machine 3, 500 megawatt on machine number 1. When I solve for the total production cost of them, it results me 54,978. So you might ask me in the examination by chance if such a question is arrived, how do you do? You can narrate the simplest possible question which will have a meritorious facts of your calculation and can justify what is best at the decision point. So therefore, a simple example will be taken. So it is what the value. And the last combination, when 3 units are combined in a simple enumeration method, then I have all the 3 can generate minimum of 150 plus 100. It is 250 250 plus 50 is called 300 megawatt is the minimum capacity what these three together can generate. The maximum capacity is add these columns 600 plus 400 plus 200 it results me 1200 megawatt. Therefore 300 to 1200 is the combination that three machines together can work in the combination load. Now the question is, how is that 550 megawatt be addressed from these three machines? Again question comes. I have to go back to the previous slide where I have fuel cost function of P1, machine 1, P2 from machine 2, P3 from machine 3. I have to solve it again. My friends, you all very clearly know when we have two machines, it's very easy to obtain economic set point using dC1 by dP1, dC2 by dP2 and equating them with a total production value of P1, P2 equal to PD. When more than two machines arise, the best analytical method is obtain the lambda itself. What is the lambda? Lambda equal to PD plus the summation of Bi by 2Ci divided by summation 1 by 2Ci. Analytic one equation we have understood in the previous semester's study. That kind of analytic lambda which we call as system lambda. System lambda need to be obtained, which is again I recite lambda equal to PD plus summation 1 to last machine Bi by 2Ci over a divider summation 1 to last machine 1 by 2Ci the coefficient if I put there I will be getting system lambda. Again you might ask me what are these A, B, C? You all know how the quadratic form of fuel cost function of a certain generator is expressed. AI plus BI PGI plus CI PGI square, where AI a fuel a coefficient independent of C, B PI it is a dependent on P1 or P2 like that, and C is dependent on square of the power like that. AI plus BI plus CI square, like these coefficients be used in your lambda calculation. Once your lambda system is calculated, using that lambda, P1, P2, P3 are calculated based on Lagrange's optimization method. What is that P1? P1 is lambda minus B1 divided by 2C1. What is P2? Lambda minus B2 by 2C2. P3 being lambda minus B3 by 2C3. I must be intelligent in understanding what value is C, what value is B, what value is A in a fuel cost function. This has to be known to us. Once I know these things, lambda I can calculate the contribution of each P1, P2, P3, then I can compute and place here. This is the placement. So for P1, P2, P3, 267, 233, 50 are the combination megawatts. And for 267, 233, 50, what is the production cost? Again I go back, use this individual equation, substitute P1, P2, P3 respectively and get the value of total cost of production from machine 1, machine 2, machine 3. Hence add it up as a grand sum which is called as total production cost of machine like that. Therefore, this is the total production cost 56,176 like that. So now you will find for your certain megawatt of 550 which is the best combination. The combination of 550 megawatt which with the 53,895 I think deserves the combination choice. We will be choosing first combination of megawatt delivery from machine 1 alone is the most economical set point. No matter when the load is ranging between 550 to 600, this machine can sustain in the plant and do it. When the load is increasing beyond 600, how can this machine be in practice? This alone cannot deliver. Then you should start hunting another combination with the machine number 1, how I should put into. Committed unit must be combined to pair with this machine so that total load can be addressed. In this way, committed units are combined in pair, one after another, to meet the requirement of the station effectively. This is how a simple enumeration method of combining the unit one after another for a megawatt, basic to the jump, basic to the next, and falling back has to be studied. So therefore, this deserves the choice. The first combination is machine 1 alone deliver the load. Then I have how this is being addressed then. This is very effective, or this study is very effective, because this kind of load curve we will find on the station. So load curve or megawatt and hours of a day, and I plot a red line show you a certain peak valley pattern. And it will be rising and falling continuously because it's being dynamic. It becomes very typical. Please see to it that minimum point, the base load. This is 450 megawatt in this representation. You must run certain generator which are called as base load sharing generator, which will run constantly to set up a certain megawatt 450 irrespective of the changes what are happening here. This is called base load generator. In between this peak and base, intermediate load, they are able to switch, take up the load and remove them as and when load is falling. You can see here load is falling flat, again load is rising, peak. It's called as peak, valley and rising pattern of load. In this due regard, certain generator of plant are put constant service. There is no impact of load variation on them. They were delivering certain megawatt continuously. We call them as base load generator. Base load generators are usually hydro, and these intermediate generators are thermal, and peaking generators are, let's say, diesel fired, pumped storage, or even nuclear, like that, which are faster in responding to the contingent changes in demand. They are able to cope up in a short duration. In that way, the load curve is addressed by the number of generators committed in a plant to suit and make the balance of peak delivery. So this is how a peak valley pattern of load on a station matters the most, to choose the combination such that such a combination of generators meet your requirement cost effectively. So it is an economic scheduling concept in which magnified view of several generators in a station. How is that the combination of committed generators are able to cope up your requirement has to be studied by method 1, method 2, like that. The first way which we saw was simple enumeration, identifying the possibilities, identifying the best possibility out of that for a certain demand has to be worked out numerically and pick the one which is cost effective in that duration. Then take another example of the same case, the same example using the brute force simple enumeration technique. When I have a load from falling from 1200 megawatt and falling down to something very low, 500 megawatt, something like that. You can just see instead of 50 megawatt, it is decreasing and increasing back. How is that the generator that you are taken here? The simple example, 1, 2, 3. How you will combine them? How you combine them to make this load pattern addressed over the period? Let's say it is a 1200 megawatt fullest capacity. What is the combination? To deal this, 600 plus 400 plus 200. All the three must run. This is the combination you are running, 1200. Suppose load is falling, 50 megawatt, 1150. Still you require them, 1200 to 800. 800 and later you require all the three on. Other way I go. When the load is 550, I can run one. When the load is more than 600, it is again I have to combine another unit. In this way, this is drawn. When the load is 500, only machine number 1 be on, rest be off. When load is 550, only one can serve. When the load is 600, only one can serve. When load is more than 600, machine 1 cannot deal this. Then I have to combine these things. In this way, in a step of 50 megawatt, this load pattern is stable into a lookup. 500, 550, 600, 650 up to fullest capacity of 1200 is put by jump of 50 megawatt. Then for a certain step load, what is the combination of generator can really meet it? This is being put by combination of unit 1, unit 2, unit 3. You can see. This is observed that from this table. When the load is, you can see, a base 600, 600 plus 400 plus 200, like this. You can just see when the load is above 1000 megawatt, 1000 megawatt and above, the red line you can see. This demand all the three generators to run. When load is 1000 megawatt up to highest of 1200, it demand all the three generators. If the load is between 600 to 1000, 1000 down the line 600, 600 to 1000, you can see 600 to 1000, it demands unit 1 plus unit 2. 1 and 2 should run. When the load is below 600, because machine 1 alone can deal this. Machine 1 is having the highest capacity 600 and it can deal up to 6. You can see up to 600, this horizontal line, load is below. Up to 600 issue, unit 1 alone can deal. 600 to 1000, 1 alone cannot. It can be combined with some other. Let us make unit 2. 1 plus 2 together can serve up to 1000. Anything more than 1000, it is the remaining machine 3 has to be combined. So, therefore, you can observe the load pattern. When the load is falling, machine 3, which is in pair, removed for a certain step of time. When the load is again falling and machine 2 is also removed. When load is going below 600, machine 1 alone is working. This step shows how low generators are eliminated from the combination. And the load is rising here. You can see load is rising up to 600, alone 1. And 600, it is still rising, 1 cannot, 1 and 2 together. It's a building, blocks like. Then again 2 can meet load with 1 up to 1000. More than 1000, 3 must be combined. This way, peak, valley, rising pattern load is addressed by a simple enumeration technique by combining certain generator in a proper manner so that such a combination is cost effective like this. It is magnified view by 50 megawatt. Jump of 50 megawatt each, it is addressed. So this is to give you how a station load pattern is very important for operational perspective to generate and meet the requirement in the jump of certain megawatt in the combination. Then similarly, I have another question. Suppose I have 3 machines. Fuel cost of machine 1, machine 2, machine 3. I have AI, BI, CI like a coefficient. And I have here something inequality constraint. P1 or machine 1 can generate minimum of 150, maximum of 600. Similar to that problem, I have this capacity. This is from Wood and Uhlenberg textbook exercise. That is one of your reference book, Wood and Uhlenberg. These presentations from the original author available on internet, completely available. Okay. So that textbook content I have referred. So therefore, unit number 1, 2, 3 with the fuel cost function with their capacity constraint. Supposed to deliver same way, an example typically 550. Let's see, 550 megawatt they want to address. How is that combination of these 3 units be worked out for a schedule of 550 megawatt in their load? Again, see how the table is formed. Unit number 1, 2, 3, 3 columns. Combination of these 3, maximum, minimum. Maximum column, minimum column. So all are off, nothing is possible. So here, off, off, on. Only 3 is on. When 3 is on, what is the maximum generation? 200. Minimum generation, 50. 200 maximum, 50 minimum. So there is a shift in column compared to the earlier discussion. Likewise, all these combinations are put in the column manner. And their combination is checked. For a 550 megawatt, can this serve? Infeasible. Can this serve maximum 200? Infeasible. Can this serve 400? Infeasible. Then alone machine 3 alone machine 2 cannot fulfill. What is the combination? Alone 1 can fulfill or combination of 2, 3 can fulfill. You can see here. This is 3 alone cannot, 2 alone cannot, but 1 alone can meet this. Among the combination, 2, 3 together can fulfill because the combination works out 600. This way, another view of the problem is done by the author and it is being put in the table, and this combinational capacities were checked with the load and solution is performed. You can see P1, P2, P3. In this combination, 2, 3 are working. So 2 can share 400, 3 can share 150. Cost of 400 production, cost of 150 production using equal incremental cost criteria. If I solve, I'll be getting the numerical solution in this way. Then total cost. Add these two. This is the cost of 400, cost of 150 on machine 2, machine 3. Add these two, total cost of combination of this row. Similarly, next row combination, next row combination, next row combination, and the last row combination. If I solve, I will have comparison of production cost for the combination. Among that, I will find this particular combination, machine 1 alone on dealing 550 deserve 5389 as a choice. This is a choice one would prefer because effectively it is cheaper among the comparison. Up to 600 megawatt, this choice be favorable. This again the same example in a different way it is being worked out to show you how witnessingly we accept this solution like that. So this is one of the another textbook problem which I have picked from the presentations of Wood and Uhlenberg presentation. Then I was speaking about how is that load curve on a station is again studied. The same thing, a peak load of a certain plant at certain duration mid 12 noon, then it is falling, again it is rising. It is to show you how load pattern on a station keeps changing. Then for this to understand, it is not intelligent targeting 1200 megawatt and keeping all the generator on entire day. For this value kind of pattern, I must eliminate, I must decrease the production so that fuel burning, fuel usage, discharge is minimized so that fuel is reserved for the future use. In this way, intelligent choices must be taken in this way. So therefore, it must be worked out carefully according to the load curve. Then this is how this kind of load curves of each station on a generating area is very important. Next. The another thing I should understand is simple shutdown rule. What do you mean by this? When I am speaking about meeting up of a load for this particular pattern on a station, I have to combine the generator to meet its peak load. I have to eliminate the load generator as the load is falling. Again, combine them as the load is rising. This is a pattern. Dynamically, I have to manage it. If a load is decreasing, how I should eliminate the generator? Which generator I have to take out of the combination in steps? The first priority to be taken out, second priority to be taken out, the last priority to be taken out are retained inside. This is called defining the generator to be taken out in a priority on the production cost. The most costlier machine which is in the combination has to be taken out first because its production cost itself is very high and sensible, has to be taken out. Hence, simple shutdown rule defines which is the generator I have to take out of the combination as the load is falling down in steps for the economic state of operation is to be defined. For that decision, simple shutdown rule says for a certain combination you are combined to generate and load. As and when load is increasing, it is to combine the generator and meet it. As and when load is decreasing, it is advisable to take out the generator which is very costlier in producing megawatt from that. We call it as equal increment cost criteria be used. Then the incremental cost of the machine which is costlier has to be taken out first. In this due regard, this results when the load is say 1200 for example, all the generator be on. When the load is decreased to 1150, let all be on. Let's see, when the load is coming to 1000 megawatt, 1200 megawatt in steps of 50 and decreasing. When the load is value by 1000, see on, off. Generator 3 is eliminated from this. What it indicates now? Why not the unit 2 is taken rather than unit 3? It is the decision at 1000 megawatt capacity from 1200. Load is falling down gradually, reach to a value 1000. It is intelligent to take out machine 3 because production cost of machine 3 and is costlier. It is combined with the 1 and 2. When the load is falling, it is best to eliminate it first. It means remaining two machines can perform better. Hence, they can share the load rather than using third machine. Eliminate this. And further load is 50 watt megawatt minus. You can see 1 and 2 can serve, keeping this off. Up to what? Can just see. Up to a combination 650. So 1000 megawatt. If load is further falling down, 15 watt minus, you will find 1 and 2 on, third off. How long? Till the combination 650 on, off. Anything less than 650, let's see, 650 to 600. Only machine 1 is on, 2 is also switched off, 3 is already switched off. Then what is the intelligence here? A value of load on the station is declining, valley, falling down greatly to a certain value 600. It is cost effective to run only generator number 1 rather than 2 in pair. 600 can be shared between these two, 300 plus 300. I can do it. It is not effective, cost effective. Hence, take out, retain this only. Then the value of load is still falling down. As you are retaining only one on, keep it on, This is called reverse process. What the process we have taken is, here, I just go here. As the load is increasing, combine 1. As the load is falling down, remove one by one, such that sustained removal is cost effective. This we call as simple shutdown. You may ask me, can this rule really result economy in operation? No. This is a simple mechanism by eliminating the cost effective or costlier machine of the combination in steps. Remaining machine will contribute to the economy of your generation. Hence, it's called as a simple shutdown rule. Simple shutdown rule will not guarantee your economy of operation. It will not result your economy. It is supportive to your decision because it looks very clearly the cost of production of the combination. When I eliminate one of the machine which is costlier, remaining two will be lesser than when it was with the other. This way, it is the simplest view. By gross way, simple shutdown rule helps. But this is not the only solution. There are so many riding factors have to be taken care before a shutdown of any generator is taken. Because is it really effective to shut down, to start again? Shutdown cost, startup cost are the two other hidden things we have to discuss. We are not yet concerned about that. Simply we are understood how is that committed units combine together to generate a certain megawatt of a demand, and how is that economic when I remove a certain costly generator remaining serve your requirement. This is the target of our understanding in unit commitment. So this shutdown rule is just a reverse process of simple enumeration concept. Then I have the another combination. So same thing is rewritten. So 1200 to 1050. How is that? All these three machines I want to be in functioning mode. Then 1000 to 650. I want only machine 1 and 2 on. This is summary. What we have discussed here is put with the blocks. Summary. This up to this range, all three I want on. This is my target to meet. Then 1000 to 600 block, black marking. So 1 and 2 must be on. You can see 1, 2 on, 1, 2 on, third off. And 600 and below, only 1 is on. This way, on a cost effective way of operation, if I do, it ensures better operation. And this is not the only solution, because so many other factors concerned have to be taken care. Next, in combination, let us brief something about this. As I say, we have done a simple enumeration method. If there are n units, 2 raised to n minus 1 combination I have to check to see to that whether it is effective or not. So there were 3 units. There are 3 units, 2 raised to 3, 8 combination. I have to check whether which combination fulfill my requirement like that. It becomes very exhaustive. Look into that. There are 50 generators. See, 2 raised to 50. So many combinations for a certain megawatt you have to calculate exhaustively in a mathematical steps. It is not that easy. It demands lot of computational time. No matter, calculations are very simple, but time required to fulfill all the steps, later decision be taken. This is called exhaustive enumeration. Hence, this is exhaustive enumeration, or brute force method is simple, but it requires lot of mathematical computation and decision to be taken. In line with this, what is being done? The other is dynamic programming method. Before going to that, let us put something, the priority listing method. What we have done here, for a certain megawatt, a step of minimum to a step value, step to another step value, I can group the generator on the priority such that the cost effective machine, the machine which I choose first, be lower in production cost, which produce a megawatt from minimum of its capacity to the fullest capacity with a very effective cost of fuel, then that is used first. When the load is increasing further, the another machine be combined, which is second by priority. Then the load is further increasing beyond the capacity of first and second choices. Then the remaining machine, third or a fourth, which is effective, shall be combined. Then it is how priority you are maintaining and you are enumerating, evaluating the state one after another to find out the cost effective sharing up of generator in the commitment schedule. This is how simple enumeration process takes place using priority listing method inside. So priority is already there. Which machine you are choosing, that's a priority by cost only. That is what is being taken. The analogous to this is simple shutdown rule. When it becomes necessary to remove the machine, shutdown rule is practiced. The last added generator, latest added generator is a very costlier one, which has to be removed first. Before that, what is added? Remove it. Before that, which is added? Remove it. Go reverse in order. So that way, the costliest generator is removed first, less costlier is maintained, and very cheaper at the end it is maintained. In this way, reverse process is done. That's what the unit commitment concept and enumeration concept and simple shutdown rule explains us.